The next item is exercise 3, where we have to prove theorem 1257. So let's start by recalling the statement of the theorem. So this was the theorem statement. Let Rn be a Euclidean space with any one of these three metrics. This is the Euclidean metric, this is the taxicab metric, and this is the subnorm metric. And let E be a subset of Rn. Then we have to prove that E is compact if and only if it's closed and bounded. One half of the claim is already with us. If we assume that E is compact, then by corollary 1256 it's closed and bounded. So now we have to prove the converse. So conversely, let E be closed and bounded. Now we have to prove that E is compact, which means what? We will take any sequence of points in E and we will prove that it has a convergent subsequence whose limit is in E. That's what we have to show. Let xi be a sequence in E. This means that each term of this sequence is a point in E. Now E is what? E is a subset of the n-dimensional Euclidean space. So each such xi will be an n-tuple like this. You can understand that we are using superscript here for the sequence terms because we want to show the components of each term somewhat nicely. We don't mix up the component numbers with the sequence term number. Okay, so this is how the ith term of the sequence looks. Now since the set E is bounded, it will be contained in some ball B with some center Z and radius R, where Z is some such n-tuple having ith component set Zi, and where R is a positive real number. Now you fix an integer j between 1 and n inclusive, that means j can be 1, j can be n, and you consider this difference, the numerical difference between xji and zj. A simple algebra shows that this is less than or equal to this, square root of this sum. You can notice that this is one of the terms here, except that it does not have the square. But if you take square on both sides, then this square will be one of the terms here. And do you see how we are getting this inequality? Because it's one of the terms here and possibly there are others and all the terms are non-negative. That's why we have this inequality. This thing, however, is the Euclidean distance between xi and z, which is less than r. Why? That's because the set E is contained in the ball centered at z having radius r, and the sequence xi is in E. So that means each term xi is in E and hence in that ball. That's why we have this inequality. So that means for each such j, this is less than r, which says that for each such j, this ordinary sequence of real numbers is now bounded. In particular, the sequence x1i is also bounded, and that is why by theorem 668 it has a convergent subsequence. You remember this theorem, this is your Bolzano-Weierstrass theorem, which says that bounded sequences of real numbers have convergent subsequences. And let this be a convergent subsequence, where say we have this suffix as I alpha, that is we have chosen some i's, where this time alpha varies from 0 to infinity. Here the index is alpha, and let the limit of this subsequence be L1, where do not forget that because the index is alpha, so now alpha approaches infinity. Also, if we now consider the second sequence x2i, that is also bounded. In particular, if you concentrate on those i's which are these I alphas, then you get a subsequence, just like this subsequence, you get a subsequence of this one, where these indices are the same as this one. That subsequence is also bounded. So now it will have a convergent subsequence of its own. That is, by theorem 668, there exists a convergent subsequence of this, which means it will look like this, x2i alpha beta. Now we are not necessarily taking all the alphas also. From them we are taking some alphas which are alpha beta. So here the index becomes beta which goes from 0 to infinity, and let the limit of this subsequence be L2. And the crucial observation is this: L1 equals the limit of x1 I alpha beta as beta approaches infinity. That is because you recall the original subsequence which was x1 I alpha, which was a subsequence of x1 I, has limit L1, and this is a subsequence of that subsequence, so it should also have that same limit. It should be convergent first of all, and the limit should also be the same. So what does this mean now? It means this: so we have found subsequences x1 I alpha beta and x2 I alpha beta, where in both of the subsequences the index is beta of these two sequences respectively, the original sequences, okay, x1i and x2i, which converge to L1 and L2, and this is important, whose indices vary over the same subset of n. As beta varies from 0 to infinity, the set over which the index of these two subsequences vary, that set has these elements I alpha beta, same thing. So that means if we continue like this, next with j equal to 3 and then j equal to 4, all the way up to j equal to n, then we will get a subsequence xj I alpha of xj I for each j, which is convergent and such that the indices of these subsequences vary over the same subset of n. And also let Lj be the limit of the jth subsequence. You may wonder why I have written only I alpha here. Ideally, I should have written I alpha, beta, gamma, and who knows how many. I mean, you can count the number, but that will be an unnecessarily complicated notation, because a subsequence of a subsequence is after all a subsequence of the original sequence. So we can write all the subsequences like just this, okay. In order to just indicate that this is a subsequence of this, you take I alpha, okay, that's enough. This involves renumbering things in a new way, but ultimately you get the point here. So we now have this fact that for each such sequence of ordinary sequence of real numbers, we have got a convergent subsequence. So you now consider this sequence x superscript I alpha, where alpha goes from 0 to infinity. Note that we no longer have any j here. That is because these are n tuples, okay. This then becomes a subsequence of the original chosen sequence xi. Why? Because of this fact. This sequence comes from those subsequences of real numbers, right? Because the indices of all of them vary over the same subset of n, that is why this has become a subsequence of this. And by proposition 12.1.18, the limit of this subsequence will be the n tuple formed by the limits of those other subsequences. I mean those subsequences of real numbers. So you now have got what? You have got a subsequence of the original sequence which is convergent. But we are not completely there yet. Is this limit inside E? That fact also is needed. And yes, that is the case, because E is not only bounded. You used the boundedness of E to find this subsequence, but E is also closed. And this is a sequence which is convergent in a closed set. So the limit needs to belong to the closed set, and that fact comes from 12.2.15b proposition. So that's it. Now we are finally there. The original sequence has a subsequence. No matter what this sequence is, it was originally a sequence of points in E that has a subsequence which converges, and that too converges to a point inside E. So that's why by definition of compactness, E is compact. So that's the solution. Do you notice how we depended fundamentally on the finite dimensionality of this situation, there are only n components. So the process we went through where we first found a subsequence and then a subsequence of a subsequence, then a subsequence of that, we were able to finally get to an end because there are only n such items. In an infinite dimensional space, this method would fail